Okay, hi everybody. So today I'm going to go ahead and go over 4.3, which is linear independence of linear algebra. So let's just jump right into it. Okay. So definition 4.3.1 states if you have S, which is the set of it's a non-empty set of vectors v1, v2, all the way up to the vr in a vector space V, then the vector equation k1 v1 plus k2 v2 plus all the way up to kr vr is equal to 0. We know that this has at least one solution, namely, we're looking for k's here, not the v's, we're looking for k's here. We know it has at least one solution, and one of them would be when all the k's are uniformly equal to 0. We call this the trivial solution, okay? Right? If all the k's are equal to 0, then it would be equal to 0 vector. Now, if it has any other solution, if it doesn't have any other solutions, then we're going to call this linearly independent set. Okay. If there are any other solutions that it potentially could have, then it's called linearly dependent set. Okay. We'll talk about what this means just down below. Okay. So example 4.3, linear independence of the standard unit vectors in Rn. So remember, in 2 space, we deal with the standard unit vectors as I and j. In 3 space, we have I, j, and k. But when you go to n space, because that's what this is, we change it because we can't just keep going with that. So we deal with them as E1, which is the vector 1, 0, 0, all the way up. E2, which is the vector of 0, 1, 0, all the way up. And then the last one is going to be En, which is the vector 0, 0, all the way up until the last one, and the last one is 1 there. Okay, so these set of vectors are going to form what's called a linearly independent set. Okay, now why is it the case? Now I'm actually not going to show it in Rn. I'm going to go ahead and show why it is so in R3. Okay, so if you consider the vectors I, j, and k, so I, which is equal to, we know the vector 1, 0, 0. J is the vector 0, 1, 0. And k is the vector 0, 0, 1. If I write a linear combination of these and set them equal to 0, so I have k1i plus k2j plus k3k is equal to 0. And if I actually write in what I, j, and k are, so k1 times 1, 0, 0, plus k2 times 0, 1, 0, plus k3 times 0, 0, 1 is equal to 0. Remember, these are just 3 vectors that are being multiplied by scalars. So I'm going to multiply them together, and I'm going to add it together. And in doing so, I'm going to have k1, k2, k3 is equal to the 0 vector, which is 0, 0, 0. And so therefore, k1 is equal to k2, which is equal to k3, which is equal to 0. And so that is the only solution here, is when they're uniformly equal to 0. So the set is linearly independent. Okay? Now, what's an example of something that's not independent? Let's go ahead and go back up here, and let's take a look at the vectors 1, 1, and the vectors 2, 2. Okay? So all I need to do is come up with some sort of a linear combination of these 2 vectors that when I add them together is equal to 0. Well, let k1 equal to -2 and k2 be equal to 1. So in doing so, I have -2 times 1, 1, plus 1 times 2, 2, and hopefully you can see how that's equal to 0. So the vectors 1, 1, and 2, 2 are linearly dependent vectors. Okay? Okay, down to example 4.3.2. So we have these 3 vectors here. There's a mistake here. I apologize for this. This should not be 10. I forgot to hit the shift key when I was entering in the closed parentheses, and it gave me 0. So this is just the vector 3, 2, 1. Okay. Now what I want to do is I want to figure out if these are linearly dependent or independent. Okay. So I'm going to write this as k times the vector v1, which is 1, -2, 3, plus k2 times the vector 5, 6, -1, plus k3 times the vector 3, 2, 1. And that should be equal to 0. Okay, now what I'm going to do is I'm going to basically add these 2 together. Now this is the 0 vector. So that's the vector 0, 0, 0. So when I expand these all and then combine the like terms, or like parts, I guess, I'm going to have k1 plus 5k2, because these are all like the first components of these vectors, plus 3k3, and that should be equal to 0. Okay, and then I go back and I have negative 2k1 plus 6k2, and then plus 2k3, it's a 2, and that should be equal to 0. And the last one is 3k1 minus k2 plus k3 should be equal to 0. Okay. Now, what I'm going to do is I'm going to rewrite this, and I don't have to. There's lots of different ways to do this. I want you to realize I'm just showing you a plethora of different ways so that you understand the problem from lots of different angles, because the more angles you see, the more perceptions you have of this problem, the better overall understanding you'll have of this problem. So I'm going to simply rewrite this as a matrix system. So I'm going to take the coefficient matrix, so 1, 5, 3, and I'm going to augment it with the solution matrix 0, 0, 0. So I have negative 2, 6, 2, 0, and I have 3, negative 1, 1, 0. Okay, just want to go back and double check, make sure I'm doing it okay. 1, 1, 2, 6, yeah. I've been making mistakes on this all day, so I just want to make sure I'm doing it fine. Okay, I'm going to go ahead and multiply the top row by 3 because I want to get rid of this 3. Okay, so in doing so, I'm going to come over here. And this is going to be the vector 3, 15, 9, 0, negative 2, 6, 2, 0, 3, negative 1, 1, 0. Okay, and then subtracting the top or the bottom from the top. And I'm going to change the top row back into its original to keep things simple. So 1, 5, 3, 0. And I have negative 2, 6, 2, 0, 3. Oh, sorry. The bottom one's going to be 3 minus 3, which gives you 0. 15 minus the negative 1, which gives you 16. 9 minus 1 gives you 8. And 0 minus 0 gives you 0. Okay, then I'm going to get rid of this negative 2. So I'm going to multiply the top by 2. So I have 2, 10, 6, 0. Negative 2, 6, 2, 0. Then 0, 16, 8, 0. Okay, add the row 1 and row 2 together. And in doing so, I have, once again, I'm changing it back to the original, 1, 5, 3, 0. And then 2 plus a negative 2 gives me 0. 10 plus 6 gives me 16. 6 plus 2 gives me 8. 0, 0, 16, 8, 0. And there we have that. Now, at this point in time, hopefully you've noticed, if you look at the bottom row and the second row, those are exactly the same thing. So what does that tell us about? So hopefully by now you've been working with matrices long enough to be able to understand this, is when we have something like this, this means that our solution set is going to be infinite. There's an infinite amount of different answers that this possibly could be. So we know that this is going to be, that there's an infinite amount of different solutions here, okay? So the set can be written as K1, and I leave this to you guys to actually figure this out, negative 1/2 t. K2 is going to be equal to negative 1/2 t, and then K3 is going to end up being equal to t. Okay, and I leave that open to you guys. Okay, so what this means, this means the solution set is non-unique. Okay, so what does that mean? This means V1, V2, V3 form a linearly dependent set. Okay, there's more than just the trivial solution, so it's linearly dependent. Okay, next page. 96. Okay, so a little bit different now. Now we have vectors in 4 space. Okay, so I'm going to go ahead and do the same thing. I'm going to take K1 times the vector V1, which is 1, 2, 2, negative 1. plus k2 times the vector 4, 9, 9, negative 4, plus k3 times the vector 5, 8, 9, negative 5. And I want that vector, or I want that equation to be equal to 0. Okay, regrouping, making my system of equations. I'm going to end up with k1 plus 4k2 plus 5k3 will be equal to 0. I'm going to have 2k1 plus 9k2 plus 8k3 will be equal to 0. I have 2k1 plus 9k2 plus 9k3 will be equal to 0. And the last one would be negative k minus 4k2 minus 5k3 is equal to 0. And then I have to figure out a way to solve this equation, the system. Okay. Now, if you look at it carefully, it's different because there's 4 rows and 3 columns. So it's an n by n matrix. It's 4 by 3 matrix. And so like it's a lot easier if it would be a square matrix. Well, if you take a look at this, what do we have? We have 4 equations and we have 3 unknowns. Typically speaking, you need 3 equations and 3 unknowns. And if you look at equation number 4 and equation number 1, those are just scalar multiples of each other, which means we have too much information. One of these are exactly the same equation. So getting rid of one of them is beneficial because it doesn't bring anything to the table. And now you have a system of 3 equations, 3 unknowns. So I'm going to rewrite this in matrix form. So the coefficient matrix would be 1, 4, 5, 2, 9, 8, 2, 9, 9 times K1, K2, K3, and that's going to be equal to 0, 0, 0. Okay. So this is all going to come down to knowing the invertibility of this, okay? Is the system going to be invertible or not? So I'm going to simply look at the determinant of this 3 by 3 matrix. Okay, so I want to know what the determinant is of 1, 4, 5, 2, 9, 8, 2, 9, 9. Well, that's equal to, I'll just take the determinant along the top row. So 1 times the determinant of 9, 8, 9, 9 minus 4 times the determinant of 2, 8, 2, 9, and then plus 5 times the determinant 2, 9, 2, 9. Okay. Going back here, when you pick 1, you get rid of that row and that column, and you're left with this, which is 9, 8, 9, 9. When you take 4, and it's always plus, minus, right? So you take 4, so you get rid of this row, this column, you're left with 2, 8, 2, 9, and then so on. Okay, so in doing this, I have 1 times, and I'm going to have 81 minus 72, which gives me 9, minus 4 times 18 minus 16, which is 2. I actually don't care what this is equal to. I just want to know, is it equal to 0 or not? And clearly 9 minus 8 is not 0. Now, what does that mean? Okay, and that's the tricky part, is trying to be able to decipher exactly what this does mean. Okay, so what does this mean? All the way back in chapter 2, we dealt, and this is in chapter 2, or actually theorem 2.3.8, which I'm trying to get to right now, right here. So theorem 2.3.8 is this, okay? These are equivalent statements. So if A is an n by n matrix, which it is, then the following are equivalent. A is invertible. We have just determined that the determinant is not 0, which means that it is invertible. So all the rest of these statements are equal to, or are true. So here it says AX equals 0 has only the trivial solution. It's invertible, therefore it only has the trivial solution. Well, what does that mean? It means the set of vectors is going to be linearly independent set of vectors. Okay? So by theorem 2.3.8, the matrix is invertible, and therefore the system has only the trivial solution. Okay, therefore V1, V2, V3 form a linearly independent set. Oh, I'm way off the page. Sorry about that. I should bring it up a little bit like this. Okay, sorry about that. Okay, example 4.3.4. Show that the set 1x, x squared, all the way up to xn is linearly independent set in Pn. Okay, so once again, you take each one of these times a constant. Because this is polynomial form, I'm going to use the letters that typically go with polynomials. So I'm going to rewrite this as a naught plus a1 x to the first plus a2 x squared plus all the way up to a n x to the n, and I know that this should be equal to 0. And this should be equal to 0 for all x. So that's what I want to find, is I want to find that what are the set of a1, a naught, a1, all the way up, that when I plug it in will make it a 0 for regardless of what the x is. Okay. Well, clearly, a naught equal to a1 equal to a2 equal to all the way up to an is equal to 0 is a solution. Okay. When you make them all equal to 0, 0 is equal to 0. And we also know by the first fundamental theorem of algebra, not calculus, algebra, that, and I'm going to call this equation 1, 1 has at most n distinct roots. Okay, that's the definition of a polynomial. Okay, we know that if the power is n, then it has n distinct roots. But that causes a problem. Why? The reason why is they say this should hold true for all x values. That means all x values are roots to that polynomial, because when you plug it in, it will be equal to 0. Okay, but equation 1 has infinitely many solutions when a0 equal to a1 equal to a2 and so on all the way up to n does not equal to 0. Okay, and that's a contradiction. So what does it mean? Okay, this implies that 1 only has the trivial solution, therefore linearly independent. Okay. Okay, next, determine whether the polynomials, and I left off some of the instructions, sorry about that, form a linearly independent set. So once again, I'm going to take actually k1, keep consistent, 1 minus x plus k2 times 5 plus 3x minus 2x squared plus k3 times 1 plus 3x minus x squared, and I know that that should be equal to 0. Okay, same thing I'm doing as before. Okay, distribute the k, group together like terms. Now this one's a little bit different though, because you're going to have constants, you're going to have x's, you're going to have x squared. So that's how I'm going to group them. I don't really care about the x's. I only want to know whether it's going to happen to make the constants be equal to 0. So I'm only going to look at the constants. So I have k1 plus 5k2 plus k3. That should be equal to 0. I also have negative k1 plus 3k2 plus 3k3 should be equal to 0. And then the last one, this is 0 because there's no x squared here. So 0 minus 2k2 minus k3 should be equal to 0 as well. Okay, so taking, and I'm going to let you guys figure this out on your own. You guys should be able to do this. If we figured out what the determinant was of the coefficient matrix 1, 5, 1, negative 1, 3, 3, 0, negative 2, negative 1, it turns out that this determinant is equal to 0. What does that mean? That means it's not invertible. Okay, So if you go back up here to where we did here, we said when it wasn't equal to 0, it was invertible, and therefore it was a linearly independent set. Now it is going to be equal to 0. So this means that the set P1, P2, P3 form a linearly dependent set. Okay, next page. Okay, so we have a lot written down here. This is written down just kind of make things go pretty fast, as we're going to have you write it down. Okay, so let S be this. Let set S with 2 or more vectors is a linearly dependent if and only if at least one of the vectors in S is expressible as a linear combination of the other vectors in S. Okay, so if you're able to do that, they're linearly dependent. They're linearly independent if no vector in S is expressible as a linear combination of the other vectors. Okay, so if one of the vectors can be expressed as a linear combination, it's dependent. If it can't be, then it's independent. Okay, as an example, in example of 4.3.2, we had these 3 vectors here, which we actually figured out was dependent. And so therefore, we should be able to write them as a linear combination of each other, which we did here. So V3 is going to be that. So V3 is going to, and by the way, this was a mistake again. Okay, there should be a parentheses, not a 0. So the vector V3, which is 3, 2, 1, should be equal to 1/2 V1. So it's a half, -1, 3 halves, plus 1/2 V2. So 5 halves, 6/2 is 3, and then -1/2. Adding these together, 1/2 plus 5 halves gives you 6 halves, which is 3. -1 plus 3 gives you 2. 3 halves minus half gives you 2 halves, or 1. So you can see 3, 2, 1 is equal to 3, 2, 1. Pretty simple. Okay, theorem 4.3.2, more on linearly independent dependent sets. Okay, so A, a finite set that contains 0, 0 being the 0 vector, is a linearly dependent set. Okay, B, a set with exactly 1 vector is linearly independent if and only that vector is not 0. That kind of plays right into what we dealt with A. And then C, a set with exactly 2 vectors is linearly independent if and only if neither vector is a scalar multiple of the other. Okay, that kind of gets back up to what we were talking about before. Okay, so we're going to prove this, but A only. Okay, just because of time, I don't want to spend all day on this proof. Okay, so what we're going to do is, sorry, just want to make sure I'm going with the same notes that I had before. For any vectors, so for any set of vectors, v1, v2, all the way up to vn, we form S, which is another set of vectors, which is going to be v1, v2, all the way up to vn, comma, 0. Okay, and that's the 0 vector, so I'm placing 0 in there. Okay, so what I want to do is I want to take up the linearly independence of it. So I'm going to rewrite it as k1 times v1 plus k2 times v2 plus all the way up to kn vn plus k, since it's a 0, I'm going to write 0, just kind of go with things, times 0, and I want to make that equal 0. So all I need to do is find a set of vectors k1, actually k0 through kn, that when I plug it in, will make this equal to 0. So that's pretty easy. We're going to let k1 equal to k2 equal to k3 equal to all the way up to kn be equal to 0 uniformly, and k0 be equal to, pick a scalar, 8. I don't know, it doesn't matter. They could be equal to 8. Now when I plug it in, I have 0 times v1, 0 times v2, plus all the way up to 0 plus vn, plus k0, I do know what that is, it's 8, times 0 vector, which is 0, and you can see that that's equal to 0. Okay, so we have just proven A. Okay, geometric interpretation of linear independence. Okay, so linear independence has the following useful geometric interpretations in R2 and R3. Okay, so two vectors in R2 or R3 are linearly independent if and only if they do not lie on the same line when they have their initial points at the origin. All that's saying is that they're parallel. This is a fancy way of saying that they're parallel. Okay? As long as they're not parallel, they should be linearly independent. Okay, the second one, three vectors in R3 now are linearly independent if and only if they do not lie in the same plane when their initial point is at the origin as well. Okay? Once again, it's like saying that they're parallel. Okay, 98. Cruising along here. Okay. Okay, so what we have, let S be the set of vectors V1 through VR be a set of vectors in Rn. If R is greater than N, so in other words, we have more vectors than this space, then S is linearly independent. Okay, so let's go ahead and prove this. So I just realized this is wrong. This should not say independent, it should say dependent. Sorry about that, you guys. Yeah, it should definitely say dependent. Because we actually did an example like that already, right? Well, okay. That problem was a little bit different. Okay, so proof. So we have V1, which is equal to, I'm going to call this V11, V12, all the way up to V1n. And then V2 is the vector V21, V22, all up to V2n. And then going down here, I have VR is equal to VR1, VR2, VRN. Okay, so those are the set of vectors. Okay, so once again, taking the set of vectors, multiplying by K1, K2, and then so on, we know we have the system V11, K1 plus V21, K2 plus all the way over to VR1, KR is equal to 0. And then also V12, K1 plus V22, K2 plus all the way over to VR2, KR is equal to 0. Okay, going down here, I'm left with V1N, K1 plus V2N, K2 plus all the way over to VRN, KR is equal to 0. Okay, so what is this? First, we have a homogeneous homogeneous system, okay, where we have n equations and R unknowns, namely K1, K2, all the way up to KR. Okay, now since R is greater than N by theorem 1.2.2, and I'll allow you guys, or I think you should go back and look up on yourself. The system has non-trivial solutions. Okay, so therefore S, which is equal to the set V1, V2, all the way to VR, is linearly dependent. Okay, example 4.3.7 showed that the set here forms a linearly dependent set on this. Okay, so once again, go ahead and take K times sine squared X, K1, plus K2 times cosine squared X, plus K3 times 5, and I'm going to make that equal to 0. Factoring, and so all I need to do is come up with a set of K values that this works out, okay? So pretty simple. If you let K1 equal to K2 equal to 5, and K3 is equal to -5, it's pretty easy to see, right? 5, 5, there's your baby, cosine squared plus sine squared. So that's 1. 1 times 5 gives you 5, and then we're going to go, should be a -1. Just jumping ahead, doing math in my head. So -1 times 5 gives you -5. So you can see 0 is equal to 0. And so these are linearly dependent. Okay, definition 4.3.3. Some of you will really like this, some others not. So here we have, if F1 is equal to F1 of X, F2 is equal to F2 of X, and then so on, all the way up to Fn, which is equal to Fn of X, are functions that are n minus 1 times differentiable. Then the determinant W of X, which is equal to F1 of X. You guys have done with this before. F prime 1 of X all the way down to F1, the nth minus 1 derivative of I at X. This is F2 of X, F2 prime of X, all the way down to Fn minus 1 of X. And you continue this over Fn of X, Fn prime of X, all the way down to Fn of the nth minus 1 derivative of I at X is called, you guys remember? The Wronskian of F1, F2, F3, all the way up to Fn. Okay, that's the one where we just took the derivatives going straight down. Okay, and then the last theorem on this page, so we'll use this later on. If the functions f1, f2, all the way to fn have n minus 1 continuous derivatives on the interval from -infinity to infinity, and if the Wronskian of these functions is not identically 0 on the interval, then these functions form a linearly independent set of vectors C n minus 1. So that's the set of functions that are n minus 1 times continuous after you take the derivative. Okay. So how is that going to help us? If you think that's a way to create a set of linearly independent functions. Okay, so next page. Okay, only a little bit left, you guys. We are on 99, right? Is that it? Oh, we only got a tiny bit left. Okay, so use the Wronskian to show that f1 of x and f2 of x are linearly independent. Okay, so we're going to take the Wronskian of x And that's going to be equal to x1 sine of x cosine of x, right? Because the derivative of x is 1, derivative of sine is cosine. And that's equal to x cosine x minus sine x, which we know can never be equal to 0. Okay? You can use your graphing calculator to solve that or whatever you want to do. Well, it can be equal to 0. I apologize for that. It can be equal to 0. Actually, can it? Oh, yeah. If x is equal to 0, 0. But it has to be uniformly equal to 0. Okay? So this expression is not uniformly equal to 0. Thus, the functions are what? Okay, so go back to the prior page. Linearly independent set of vectors. Okay, are linearly independent. Okay, use the Wronskian to show that F1 through all this are linearly independent again. So 1, 0, 0, e to the x, e to the x, e to the x, e to the 2x, 2e to the 2x, and then 4e to the 2x. And then I'm going to go ahead and take the determinant of this. The easiest one to do is take it along this column. So it's really just 1 times that. It's equal to 1 times 4e to the 3x minus 2e to the 3x, which is equal to 2e to the 3x, which will never be equal to 0. Ever. You can't plug something in for x there and make e to the x equal to 0. So, therefore, f1, f2, f3 for a linearly independent set. Okay, and that is it. Okay, so looking at the homework, I just wanted to talk about 2 of them. 4 and number 5, make sure you get busy working on those early. They are proofs, and those usually take a little bit of time to work through. Okay, okay, so that's all we got. Thank you so much, everybody, for today, and we'll see you later. Bye, everybody.